one of the things I did at one of the schools, and it's a $20 coffee card.
Oh yeah.
So I thought the best thing to do is, being as I'm not into drinking coffee and wouldn't go there anyway, it would be to auction it off.
To auction it off?
Yeah. And then the money goes to the RASC.
It'd have to be fairly informal auction because racing is fairly normal. We need a license.
Oh,
So
yeah.
you should probably give it to Sid. Where's Sid gone?
Well, I can do it.
What, right tonight?
Yeah. Just before the meeting starts.
You want to do it right now?
Yeah. I'll do a $5 reserve on it, and I'll just shout at everybody.
Or do you want to just save it for a couple of minutes, maybe under the other part down there?
Okay, sure.
Because we have a visiting
That
guest.
works too.
Yeah, it works.
Yeah.
See down,
Put it wherever you like.
maybe down here under new business or
Okay.
other.
Whatever you think best. I'll grab a seat close at hand.
You're hired. Okay, everybody. Okay, so we are the RASC Victoria Center. Do we have any visitors or newcomers tonight? Well, I know we have one visitor, so Dr. Batten is going to introduce a visiting astronomer from New Zealand.
Yes, I'd just like to let you know that you have a visitor here from the Wellington Astronomical Society in New Zealand. 20 years ago, I had a temporary appointment in New Zealand, and in those days, the Royal Astronomical Society of New Zealand was organized very much like our society. Roger Patland, who is our visitor, tells me it's a little different now, but he is a member of the New Zealand astronomical community. He is an amateur astronomer, but he is working with a colleague and friend of mine, Ed Budding, who is a professional astronomer who is now emeritus at the Victoria University of Wellington. And so I'd like you to know that Roger is here, and ask you to welcome him. And Roger, perhaps you'll stand up so people will know who you are.
So welcome. If you have any questions or anything you want to ask from us, just go ahead.
My greetings from Wellington, New Zealand. Thank you.
So on to the business part. You'll notice my report is in the Sky News as usual, and it's online. No need to bore you with the white noise that I usually post up there. Let's get Joy's report. Do you have anything to report for us, Joy?
No, the minutes are up to date. They should be online for our last month.
Yeah, I read them. I saw them. Yeah. Good job. Thanks. Okay, Bruce.
Our current count is in pretty nice shape. Our member count stands at 12,628. Our meeting count is 1,920.
Wow.
So, and right now we're just looking for ways to spend it. So.
I'd like to talk about it.
With any advice that are for the benefit of all, and just bring those, move those along to any member of council, and we'll start thinking about acting on some of this ideas. That's pretty much where we're at. Oh, we've got end of the month. Be another event out at Cal Point. Got 2 in a row now. The weather's actually been good enough for it. We might even make it 3 in a row if the weather smiles upon us.
I have a call from a lady who's got some visiting Japanese exchange students who might want to come and see you on that night.
Okay. You give my email for the treasurer.
I did actually. So she might actually be contacting you sometime really soon about that. Okay, Chris.
So we have 209 members at the moment. About 22 people's membership is in the grace period, meaning it's expired. So, plus or minus, we're probably holding our own.
That's pretty good. 209 is actually really quite good. Yeah. So make sure you get your renewals in on time.
So if you're one of those 22 people, please.
Okay, Start Party, good news. you might have read it in my report that we've chosen to waive our Star Party fee again this year. So Star Party is ours for August 21st to 23rd. So it's a go. And on a side note, Machosen has also passed their light pollution bylaw officially now. So good news on 2 counts from my part of the world. Sid.
Public outreach efforts, thanks to Lori and all the volunteers who helped. The latest, after last month's meeting, we did about 4 different groups, thanks to Ruth for taking over the night sky viewing at Monterey Middle School, and Bruce and all his volunteers. It was a great evening, and we also went night sky viewing Monterey Pathfinders behind the Oak Bay Fire Hall. And that was very successful, except Dorothy lost her car keys. I hope it was not.
That's ancient history.
Oh, it happened just yesterday. Anyway, thanks
And
to
then,
all
by the
the
way, the brownies were there too. It wasn't just the Pathfinders. because-
brownies and Pathfinder. Anyway, the big event coming for us is April 25th. If I have not been in touch with you for volunteering at the museum, please get in touch with me, because we need more volunteers for Astronomy Day at the museum on April 25th. It's a all-day event from 10 a.m. to 4 p.m. Then we are hoping that we will be going to the CU for public night sky viewing for the public.
No word on that yet, I guess?
Well, it's going to
No,
happen.
it's still not
It's not fully
signed,
up.
sealed, and delivered, but I'll see if I can get something.
Yeah, otherwise we might have to plan for some other locations. Cattle Point could be a possibility, yeah. And just for your general information, that we have had 4267 Galileo moments since September 1st. And the number of volunteers contributing to that effort, 59. And total volunteer hours, I usually keep track of it, almost 500 volunteers hours since September. So that's a great effort from our group. Thank you for everyone who helps. And if you would like to help for Astronomy Day, please get in touch with me. And also we are raffling. That's another news which we need to spread out. We already got some raffle tickets sold now, but if you want to buy raffle tickets, it's contributing to our public outreach efforts. So please come and see me. What's the prize? Oh, the prize is a beautiful gold-plated Celestron Starbright XLT with equatorial mount with a go-to pedal, and you will love it. So come and see me.
Gold plated.
If you have any questions, volunteering, or you want to buy reference, please come and see me. Thanks.
Thanks, Sid. Joe, website?
The website is operating normally. I don't think there's any news, which is good news with the website. Matt may have a few other things to talk about with the technical infrastructure, but it's running well. The latest minutes are posted in members-only area, so very good.
Good, thanks, Joe. And in case you didn't know, we had a little change of council last month, and Joe has agreed to take over as acting vice president, at least for the short term. So thank you, Joe. Yes, thank you. What I do need though is someone who would maybe want to do that job, at least for maybe from September onwards for the next year and a half on an official basis. So if anybody has any ideas they might like to join council, come down and let me know. There's really not an awful lot involved. All we really need on that thing is to get the same kind of high quality guest speakers that Joe has like lined up for us tonight, for instance. And that's really the main task of the VP right now. There's some other minor ones, but that's kind of the main thing we need to do is get good high quality guest speakers for the monthly meetings. So if you think you might like to be on council, come see me or shoot me an email. Matt, tech stuff.
Next up, is that what I do here? Let's start off with a little bit of analytics from last month. We had 1,200 visitors to the main site, 374 to the Zenfolio site, average of about 2 minutes on each page, which is pretty consistent. VCO is swimming along. We temporarily put on the Hyperstar on the mean 14-inch. Found that it was not cooperating because of the mechanics of the focusing mechanism on the 14-inch being a pivot and thereby not keeping collimation. It was a very, very frustrating process for us and to use it for photography, which is what the Hyperstar does and the only thing it does. So we're looking at other options in the future there. Part of which was a grant that Dan and I, emphasis on Dan, did a lot of legwork on through the CIRA, the Canadian Internet Registry Association. They have a community outreach, community involvement investment program where they are looking for technology focusing on the internet to benefit Canadians. This is exactly what the VCO needs to be. Broadcast live, broadcast interactive, and broadcast to schools, and create all kinds of static as well as live presentations. So maybe Dan could say a word or two more about that.
All right. So let's see. So what we've got is we've laid out a program to integrate the VCO and regular observing into the current outreach program going to schools and the public. And the idea of that is that it's very difficult to get everybody out to an event on a clear night. And, you know, even if you do manage to get a lot of public interaction, parents usually aren't going to be able to make it out there with their children at, say, 9 o'clock on the school field. And you're going to have lineups anyway. So this way, just using a simple internet browser, you can hop on something like YouTube and then take part in the observation by being able to leave a comment and say, hey, I want to see Mars. And then they can probably say, hey, it's on right now, try again in 5 months. But, you know, people can take part in it. And so what we've done is we've submitted a proposal that will include internet and VCO and a bunch of new optical systems that we picked out so that we could get the best out of this experience for users. So within that, we're looking at turfing the need and going up to a 17-inch plane wave telescope and getting a monochrome CCD so we can also do some, you know, in work and or narrowband work, whatever people are interested in during broadcasts with filters on.
We're missing also a live video camera from Point Imaging, which has either 120 frames per second or 60 frames a second in pretty darn good quality. It's a color camera, obviously these plans, if you want the color theme. The benefit of monochrome camera for stills just cannot be emphasized enough. We are planning on keeping around the existing camera, which is a single shot color. If we get this grant, there's no real need to sell it. And so we still, for the membership, have an easy single shot color. But in terms of getting color out of that equipment, it was never very easy in the first place. So a monochrome camera allows us to do all kinds of interesting things with an 8-position filter wheel that can have
and an auto guider built in.
And an auto guider built in. So all kinds of very high-end equipment that would make this pilot program work really well. The scope of the grant is funding for 1 year's worth of activity, after which time we would have to approach whoever our internet service provider would be to get an ongoing commitment of support from them. But I think once we demonstrate what we can do with this, we won't have much trouble. That's the hope.
It's exciting on a whole bunch of different levels, but to be able to operate from the VCO directly into classrooms is very cool.
Is that those what we're looking at, one of the focus that comes up the axis? The altitude axis, Naismith focus?
No, it's a corrected diagram. So it's,
Yeah. And some of them, anyway, maybe it's the larger one. It's a bigger one that has the axis on the altitude.
yeah, no, I don't think so. I think this one's just straight up flat. Yeah, at least that's what it looks like.
The value of the request?
$44,420.
And there's an option to, if they don't see the value in that, there's an option to go down 25% or something, which still leaves us in good shape with just a slightly smaller telescope.
What are you planning on doing for an internet access?
The plan would be, the only difficulty with internet access at the VCO has been access to the telephone poles and the equipment that is currently on the telephone poles. I have written authorization to have a wireless point-to-point network with one end being at the VCO site. So the intention would be to get a subscription with an internet service provider and have them install equipment on some common property, being the telephone pole down below the hill or on somebody's residence.
So you could bypass the bill.
Yeah, exactly, bypass the hill. And this is a proven technology that will deliver far more than we ever need in terms of throughput. Other
To meet stuff.
So would it be advantageous to have co-funding from the center to do some fraction of this?
So a portion of the budget that we put forward to the proposal included, what did we land on?
I think 1,500.
1,500 from the center. As well as, what's the word for that? The volunteer. In-kind contributions of many hours. So it all added up.
Because you guys are worth $60 an hour.
I think we only put it in at, what was it, 25? So.
I figured my TA rate was
So when are we going to know? Is it May? Late May?
We hear in May, and I already did hear that they accepted the application. So. It's this year.
Well, good job, you guys. I read over that proposal. It was awesome. Okay, let's get a bit of giddy up on here. This one here, coming up Friday is our next night upstairs on the 32-inch telescope. The weather's kind of looking a bit iffy. Are you in town on Friday? Would you like to join us? Have you been to the telescope upstairs? Not here? Oh, you're welcome to join us if you like. Yeah.
It's a real pretty, so I feel like
Yeah, if you like, at the end of the meeting, just come and see me and I'll explain how it all goes. And then you can maybe come up and join us on Friday night. So hopefully we'll be on Friday night, the weather will be clear because it'll be nice to use that. And I got this email directly out of the blue, just like it just fell into my lap from Dave Balin asking if we wanted 3 nights on the Plaskett in the next quarter. No, and of course nobody does want that at all. So I just said, no, forget it. So I kind of stopped drilling on my keyboard and long enough to type in that reply saying, oh, yes, please. And I haven't heard back yet. So hopefully sometime in the next quarter, which I guess we've just started, or we'll start soon, we'll get 3 nights on the Plaskett. They may not be like guaranteed to be Friday or Saturday nights, but hopefully we'll get 3 nights on the Plaskett. So find your memory sticks and think of targets that you want to shoot, and hopefully we'll get 3 nights on the Plaskett as well. So national, Michael, come on up.
Okay.
Michael's got something for us.
I did a solar observing thing for a bunch of people about this tall. As a thank you, I was given a card. I think it's worth $20 to Habit Cafe, the Atrium location, 808 Yates Street. So I'm going to auction it off, and the money goes to the kitty. That's mine. We'll start at $5 because that's what I'd pay for it. Do I hear 6? 6? Come on, hands up. Who wants a 6? 6. We have 6. 7. Who has 7? 7? 7? 7? Do we have 7? Okay, we're going for 8. Let's have 8. Do I hear 8? I have 8. 9. 10? 10? We have 10. 11? Who wants it for 11? $11. $11 going once. And $10 going once. 10 going twice. You got it.
Laurie, national issues?
Don't give it to the press. There you go. Just friendly.
All right.
Bad idea. Bad idea.
So our next large meeting for the at the national level is going to be on Saturday, the 21st of March, and it will be via teleconferencing. So we'll be doing that, going over quite a lot of the work that will be needed in order to get ready for the main big meeting that will be at the end in July, between July 1st and July 5th in Halifax. So again, I'm going to ask if anybody is interested in coming up to Halifax. There'll be a few of us coming, and we'd love to have a group of people come out to the main meeting there. The only other thing that I meant to ask about last month was that we've been asked to talk a little bit about the national awards that are given at the national level for a variety of things like the chant medal that is given for research. There is a medal that, an award that's given for long service. There's an award that's given strictly by the president of the association that is simply done by the president. Actually, Sid Sidhu won that award a few years ago from ours. But we have a tendency here in Victoria to not put ourselves forward in putting ourselves up for national awards. We might be a little shy about the things that we do here, but we need to kind of pull ourselves into the national level. So I'm just offering that suggestion that if anybody is interested in not going on the website and nominating someone for a national award, I think that we've got some pretty good people that we could put forward for a variety of things. If anybody has any ideas, or they'd like to talk to me about what will be going on, or what I can give to the national on the 21st, please let me know. The only other thing, Dorothy, did you want to talk about the science fair?
I'm not sure there's anything more to say, except that this is, I think, an opportunity that we have in education across grades from 4th to 12th to make more contact for all the sciences that RASC supports. So it's astronomy, cosmology, space exploration. It's also the whole shmoo of life on Earth.
Yeah.
And there are a lot of topics that students pick out that could be much improved and certainly appropriate for us to consider, and they just don't have this background. We've been very minor in our sponsorship awards, and I think we can let the students, they come back here every year, so talking to students 1 year about what they do, if they have a project that they don't see could be much better if they included something either about the sky, animals at night, or whatever is appropriate, that we can do a lot simply, and it is a lot of fun.
Sunday, April the 12th, and we will be doing general judging, but then the special awards, anybody can come and be a judge, come and look at the projects and come up with some things. So if you're interested, either talk to Dorothy and I.
What science fair is this?
It's called the Vancouver Island Regional Science Fair. So it's held here. No, sorry, in the LA building. In the LA building.
It's the big one.
It's the big one. This is the big one, yeah, for grades 4 to 12.
Good, thanks.
An email to Sherry this afternoon, recommended you may not have seen it, some more details about special sponsors, so.
Anything else? Any questions, new business to bring up? Greg?
We're interested in doing the marathon possibly that weekend at all.
The Messy Marathon?
Yeah.
It's on. It's a go as far as I know. Did you not get Michelle's emails?
Well, I last heard that it was sort of, you have enough people that were interested.
Well, as far as I know, it's a go. We have 3 people.
Michelle just sent me an email an hour ago saying that it is on for Saturday, March 21st.
There you go.
What time are they gonna be at the gate at?
I expect that'll be announced on the active service list closer to the date.
Anything else? Okay, thanks, Joe. And Dr. Allison?
She'll have her own. Well, this evening we have a great speaker, Dr. Sarah Ellison, works here at UVic. She started at UVic in 2009. You're Victorian now.
I am now Canadian, even.
Canadian,
Yes.
Great stuff. With her husband, John Willis. I was just looking at her CV before I came here to the meeting, and I realized that she has a passion for travel just like I do. So that's certainly a plus when you visit more than 60 countries. She's also a painter. She swims. She does triathlon. She runs. My goodness.
Occasionally I do astronomy as well.
Yeah, you're supposed to be doing astronomy. I know you have to fit it in there sometimes. And also, probably the most important thing from my perspective is she's a great friend of RASC Victoria Centre. Certainly, starting with International Year of Astronomy 2009 was a great effort by everyone, including UVic. Thank you very much for that, because that was a big deal for everyone. Tonight, Sarah's going to talk to us about galaxy mergers and what they can lead to with star formation and black holes. I give it over to you.
Great, thank you, Joe. I'm not going to apologise. Oh, so apologise in advance. I'm sort of semi-hoarse at the moment. I'm recovering from a bit of a cold, and I already gave one public lecture today, which decimated part of my voice, and this may well do me for the rest of it. Okay, so I'm going to talk to you tonight about some of the lessons that we've learned about galaxy mergers over the last few years. So a lot of this talk is going to be background material and context and nice pictures as well. But I'm also going to try to give you a hint of the research that's being done in this area. So we'll try and find that balance for us. So note on galaxy mergers would be complete without a nod to this gentleman, Chip Arp. He is in some sense the godfather of galaxy mergers. So Arp put together an atlas of peculiar galaxies back in 1966. And there's actually a very nice book that you can now buy. I have a copy of this book. I can vouch for it. It's put together by two amateur astronomers who have photographed the Arc galaxies and put them together in this nice book. And in addition to the photographs they've taken, they detailed the technical components of their photographs, so the details of their telescopes, the exposure times, F ratios, and all this kind of thing. So it's actually a very nice observer's guide slash content, in addition to being able to see the nice pictures. You can also see pictures of all the peculiar art galaxies in an online catalogue. I've given you some links here. So at the bottom, this is a link to actually the book that you can see here. If you are keen to try your hand at observing some of these peculiar galaxies yourself, there is an artgalaxy.com that you can go to for tips for that. But there's also this iPad Caltech site where you can read the original preface by Art to his atlas, and also see photographs, plate photographs of these galaxies too. So since it's well known that amateur astronomers are much better than professional astronomers at actually knowing what we're looking at in the night sky, we're going to play some kind of galaxy merger bingo here. So, easy one first. The easiest first, which is this one. You don't have to know the ARP number, but do you know the name of this one? The antenna galaxy. This is ARP 244. I never know the ARP numbers, but this one is famous enough to have its own name, the antenna galaxy. So this is actually, it's two galaxies that are in a fairly late stage of the merger process. So two originally disk galaxies, now the morphologies are kind of disturbed, but the one disk up here and another one down here. We're going to see a zoomed out version of the antenna in a few slides' time. This is really just looking at the inner part. Now this picture of the antenna galaxies already gives us a hint of some of the interesting things that we're going to see going on in merger galaxies. So, as I say, one of the spiral galaxies is down here and the other one is up here, but there's this bridge of material between the two. And you can see in this photograph, there's a lot of bright emission coming from that bridge. And it looks pink in this picture because it's tracing new star formation. We're going to see that galaxy mergers are actually very good at triggering new bursts of star formation. Well, this is a trickier one. Most professional astronomers wouldn't get this. Does anybody know it? Okay, this is ARC 238. So in this image, we've got the galaxies not quite so close together. So we're catching them at an earlier time in their duet. The fact that we can see not only the two galaxies are separated, but we can see these lovely long tidal tails, we call them. So what has happened here is the galaxies have come past one another. They've had a close passage, and as they move apart, material has been pulled off in these long tidal features, and they're sort of tracing the orbit that these two galaxies have moved on. This is another spectacular one. So in this case, what we think has happened is the galaxy on the left has moved with a very high velocity through the center of the galaxy on the right. So this is ARC 147. This was actually observed even as early as the 1890s. This was identified, one of the earliest merger galaxies that have been identified. And so because the galaxy on the left approached at such a high velocity, it really just punched a hole through the center of what was originally a beautiful spiral. We don't really see the spiral disk left anymore, but you can maybe see down here it's more orange-like compared to the rest of it. So it's thought that this is now the remnant of the original bulge of that spiral. And there's actually a lovely compilation that HST have put together that I put a link to here. At the end of this talk, I will maybe send Joe a PDF of this file so that if anybody is interested and doesn't have the chance to scribble down all of these websites, then they can go to the market. But galaxy mergers are very popular objects to point Hubble at for making public images because they're such dramatic objects. Okay, so Art put together this atlas of several hundred peculiar galaxies. Some of them were very dramatic cases like this. Some were much more subtly peculiar. Maybe they were just a little bit lopsided or a spiral with just one arm. And what Art was trying to do when he put this catalogue together, it was not his goal to try to be complete in any way. He was just trying to pull out strange examples from the galaxy world to try to give observers something to explain. So in order to understand the process of galaxy evolution, often it's useful to catch galaxies when they're doing something strange and to understand then the process that is causing this strangeness. So this was Art's goal in putting together this catalogue. So it was really kind of phenomenological in the sense that there was not a huge amount of scientific understanding underpinning this catalogue. Arguably the first astronomers to really start understanding what we were seeing with these peculiar galaxies were the Toomey brothers. So these brothers, Yuri and Alan, were particularly famous for the first simulations of galaxy mergers. So nowadays, when we make simulations of galaxies, or when we try to make big cosmological simulations of the universe, we have millions and millions of particles, and we have very, very high resolution. But back in the 1960s and 1970s, obviously, computer power is a lot more limited. And so the number of particles, the number of stars that you could put into these simulations was on the order of a few hundred or 1,000 or so. But essentially, the process was the same. The idea was that you built a galaxy with particles in it to represent not so much individual stars because the masses of the particles were too small, but let's say clusters of stars. And then when you had your two nice stable galaxies, you just sent them on an orbit towards one another and let gravity do its thing and see what happened. So that's what the Toomey brothers did in the early 1970s, and they were particularly proud of this computer simulation. So each of the points that you can see here, these are one of the particles in their computer simulation. And so they sent these two disk galaxies on a collision course towards one another. And this was one of the snapshots that they got out of their computer simulation. And they're particularly proud of this because it bore a striking resemblance to what we see in the antenna galaxy. So this is now the same merger that I showed you on that very first slide. I'm zoomed in on just this central part, but here are the long tidal features that are present as well. So this was really a breakthrough because it allowed us to understand that very many of these peculiar galaxies in Arc's catalogue were likely involved or had been involved in some kind of interaction. The other very interesting thing that the Toomey brothers noted, and again this was very prescient and profound for its time, was that if you counted up the number of galaxies in the nearby universe that are in some kind of interaction, that number is about 1 or 2%. And then if you look at the fraction of galaxies that are now elliptical galaxies, and if you posit that all galaxies started off as some kind of small dwarf that built up to a spiral galaxy, this merger rate was enough to account for all the ellipticals that we see today. So this was the first time people had suggested that maybe galaxy mergers played a really important role in a galaxy's history, in transforming galaxies that were originally spirals into ellipticals, and that's one of the basic pictures that we have of galaxy evolution today. The Toomey brothers are also famous for developing this sort of qualitative sequence called the Toomey sequence. The Toomey sequence is really classifying galaxies at different stages of the merger. So here's the sequence. These are different galaxies, real galaxies, so not simulated galaxies, that are being caught at different times of the interaction. So these mergers in real life take hundreds of millions of years, maybe even billions of years, to go from a close past to a final coalescence. So we don't see this playing out in real life. If we want to understand how galaxy mergers are going to affect a galaxy, we have to catch different galaxies at different stages of the interaction. So here we've got a pair of galaxies that don't look disturbed in any way. They look nice, regular galaxies. So these are galaxies that are probably approaching one another for the first time. So the kind of tidal disturbances that we see and when morphologies get messed up, that only happens after the first pass. As they're coming in towards one another, they sort of have no idea what's coming in. Wow. Okay, so now here's a closer pair. They still don't look disturbed, so this pair is probably also not yet had its first, we call this a pericenter, and it has a close passage. These are one of the pairs I showed you on the earlier slide. So this pair has now had a passage, and it's likely moving apart when we start to see these tidal features, and the dead giveaway that something interesting is going on. And then the rest of the sequence is really just stepping forward in time up until the point where the two individual galaxies are barely distinguishable anymore, all the way up to what we call a post-merger. So when the two galaxies have fully coalesced. So this is the two-way sequence. On the observational side, so the two-way brothers were working on the simulation of galaxies. On the observational side, the big steps forward in the 1970s were to start comparing the properties of some of these peculiar galaxies with normal galaxies. So this is a graph that's taken from a paper published in 1979 by Larson and Tinsley. And there are two panels here. So on the left-hand panel, the galaxies represented by the points on that left-hand panel are from the Hubble Atlas. So these are, you can think of these as normal galaxies, well-behaved galaxies that are rather isolated from any other object. And on the right-hand side, the points on that panel are represented galaxies taken from the Arc Atlas. So these peculiar galaxies, which we now know to be large mergers. Okay, now what's being plotted here is color on both axes. So B minus V color. So you take the magnitude in the B band, you take the magnitude in the V band, subtract one from the other, and the same on the y-axis. So there's a different color that's plotted on the y-axis. And the first thing that you can see is just the scatter of points is much greater for the peculiar galaxies than for the Hubble galaxies. So normal galaxies follow a nice, well-behaved trend in color space. Color tells us about a number of things. It can tell us about the mass of the galaxy. It can tell us about how many stars have been caught in the galaxy. Okay, so there's a larger scatter. In particular, this scatter is upwards. This black line is the same in both panels. So you can see that there is a larger scatter upwards for these peculiar galaxies, and that vertical upwards direction is scattering towards bluer colors. Okay, so what Larson and Tinsley was seeing was a larger scatter in colors and particularly a shift towards the blue. Now this was the first observational hint that these galaxy mergers might be responsible for producing new stars. These new stars are showing up in the blue wavelengths. Okay, so that's the sort of historical context of this work, and now I'm going to tell you something about modern observations of galaxy mergers. So I've already said that about 1% of nearby galaxies have either a close companion right now or show signs of having recently interacted with something. So sometimes a galaxy can come past, it can have a close passage and mess things up, but it doesn't actually get captured and it just moves on past. So we should be interested in this phenomenon for a few reasons. So first of all, even though it might seem that the distance between galaxies is very great, 1% is not negligible. If somebody told me I had a 1% chance of winning the lottery this week, I'd be out there buying tickets. So these things are, not insignificant in terms of their occurrence. And they seem to be responsible for some of the most dramatic events in a galaxy's life. So to show you that, I'm showing you've got two mosaics of galaxies here. On the left-hand side, I'm showing you a mosaic of a certain kind of galaxy that we call an ultra-luminous infrared galaxy, which is kind of a mouthful. We call them ULIRGs for short. So what's a ULIRG? A ULIRG is just defined as having a certain luminosity in the infrared. So if we add up all the photons throughout the mid and the far infrared, and we turn that into a solar luminosity, so we compare it to the sun's luminosity. If that whole galaxy has more than 1 trillion times the sun's luminosity in the infrared, we call it a ULIRG. It's maybe hard to kind of get a perspective on that number, 1 trillion times the sun's luminosity, but this is a very, very, very luminous galaxy. Okay, so if we look at this compilation of ULIRGs in the nearby universe, we can immediately see that these do not look like normal galaxies. They do not look like nice, well-behaved spiral galaxies or nice, smooth elliptical galaxies. They are clearly either disturbed in some way, or they have a close companion with which they seem to be interacting right now. So these very, very luminous galaxies seem to be preferentially picking out galaxy mergers. So the first thing we should ask ourselves is, what's making these galaxies so luminous in the infrared? Well, the answer is extremely high rates of star formation. So to give you a sense of the typical star formation rate of a galaxy, our Milky Way galaxy has a star formation rate of about 1 solar mass per year. So our Milky Way galaxy, on average, is making 1 new sun's mass worth of stars every year. It's not particularly impressive when you think about it. These things are making hundreds or thousands of solar masses of new stars every year. So that very high rate of new stars means they're pumping out lots and lots of very high energy photons, and those high energy photons interact with dust. So the dust gets heated up and then it emits in the infrared. So that's why they're so bright in the infrared. So these very luminous infrared galaxies must have these very, very high rates of star formation. Okay, so this is the first lesson. Mergers seem to be responsible for galaxies with the highest star formation rates in the nearby universe. Okay, on the right-hand panel, it's another 9 galaxies that I selected, a different 9. These 9 I have selected not because of their properties, their stellar properties, but because they seem to have in their centers a very rapidly accreting and luminous black hole. Okay, so these are what we call quasars or QSOs. So when we look to see what are the galaxies in which we see these very luminous black holes, excuse me, we can again see that many of these host galaxies either have a close companion or they're disturbed in some way. So once again, when we take this extreme property, in this case, that the black hole is very, very actively guzzling material, we again see that mergers seem to be implicated in that. All right, so let's now take a look at a movie to try to understand why mergers can give us these extreme events. What I'm going to show you is a computer simulation of 2 galaxies. They're essentially copies of one another. And we're going to see this color-coded view of the galaxies, and it's color-coded by how much gas there is in different places. So we set these galaxies moving towards one another. They have this close pericentric passage. They move apart, they form these tidal features that I've talked about. They reach some maximum separation, and then they come back in again. I'm going to run this movie a few times. So galaxies can have a few passages before they eventually spiral in and merge and give us that final post-merger. Now, when I run the movie a second time, we're going to look out for a very particular feature. What happens in these interactions is that the gravitational torques that the galaxy feels creates a bar through the center. Now, I'm sure you've all seen pictures of barred galaxies. So this interaction stirs up this bar in the center of the galaxy. Now, this is really important because what happens is, even though I'm going to show you the movie of the gas, if I showed you a movie of the stars as well, we'd see that there's both a gas bar and there's a stellar bar as well. It just happens the two things are not quite aligned, so they pull on one another. And that pulling drains energy from the gas and makes it flow towards the center. So let me run the movie again. So the presence of this bar means that gas can flow along it to the center. So gas piles up in the center of the galaxy. Okay, we're going to see the bar forming in a minute here. Okay, and the same in the other one. So what that means is that there's a very effective mechanism in these galaxy mergers to move gas to the center. Now, we know that the amount of stars we make depends on the density of the gas that's present. So when you pile up all of this gas in the center of the galaxy, you predict a starburst. Moving that gas to the center of the galaxy also means you have fuel to pour on to the central black hole. So you can now create a luminous quasar as well. So simulations such as these can predict what we should expect to see in the observations. So I'm showing you here a couple of plots from research papers from a few years ago that have run these kinds of simulations. And what they do is they count up where the particles are moving in the galaxy and what they're doing, whether they're forming stars, whether they're falling onto the black hole. So we can see some snapshots of the galaxy that correspond to different times. So this axis here is time. So we're moving from the galaxies are just coming in, and then they have their first close pass corresponding to this dashed line here. So this top panel is separation. Okay? So they're coming in, they reach some minimum separations, they have their close pass. They move out again, now they've got these tidal features associated with them. They have another close pass, they move out, but not so far this time, and then they finally merge. Just as it's the same movie that I just showed you. And then if you take a look at this lower panel here, this is measuring the change in the star formation rate in these galaxies and mergers. And it's being compared to what you would see if you took the same galaxy and just left it in isolation. So what the simulators do is they map, they measure the star formation that forms in their isolated galaxy, and then they do the same thing in their merger. And if we had no difference in the star formation, we would just see a flat line along here, because this axis is, what I get in my merger relative to what I get in my isolated. So if nothing interesting was happening, this would just be a flat line. And sure enough, you can see that before they move past one another, that's what we have. As I mentioned earlier, nothing happens until they've had that first close pass. But once they've had that close pass, we trigger that bar, gas gets sent to the center, and we see the star formation rate start to increase above what we would expect in an isolated galaxy. That star formation then dies down again, and then close to this final merger, we get a really big burst of star formation. We see the same thing if we look at the rate at which gas is falling on to the central supermassive black hole. So you put a black hole in your simulations, and then you just measure how much material is making it all the way down to the center. So that's what this middle panel is showing. So it's the same idea. We're looking as a function of time, what's going on. So this is the accretion, this BHAR, this just stands for black hole accretion. It's just measuring how much gas is falling onto the black hole. Don't worry too much about different curves. All I want you to see is that there is an increase. Again, these galaxy mergers seem to be able to pour gas onto the black hole. Okay, well that's all well and good. The simulators, the theorists are feeling pretty pleased with themselves, and they go away, they have a beer. But we need to actually demonstrate that this has some reality. We need to check to see whether we can actually see these kinds of effects. Okay, so then the observers among us like to go out and test these predictions. All right, so what we need to do is we need to assemble a sample of galaxy mergers so we can actually test this thing. Okay, so how are we going to assemble our sample of galaxy mergers? So, I've said to you this is around 1% of the nearby universe, and 1% is really not insignificant, but, it's not super common either. So we need to have a large survey of galaxies from which we can select these mergers. And we'd like to have a large number of these galaxy mergers so that we can do a really good job on the statistics. Because if we just look at one or two, you can get freaks of nature and it doesn't really tell you anything robust. So you want to have a large sample of these galaxy mergers. So you have a large sample of galaxies to select them from. So this is the survey that we have been working with. It's a survey called the Sloan Digital Sky Survey. Some of you might have heard about it. It's been around for a long time now. It started off in 2000, and in its first incarnation, it ran for about 8 years. And it was responsible for mapping about 1/4 of the night sky. There have since been follow-ups to the original Sloan survey. And this is a map showing the positions of all of the galaxies that have been detected throughout these different Sloan surveys. So this is a map of right ascension around the sky, and then from the center out, this is a measure of distance from us, so the redshift. And each point on this graph is one galaxy. So this is the telescope that made the survey. It's a 2.5 meter telescope at the Apache Point Observatory in New Mexico, in the southern part of the US. And it had 2 parts to the survey. The first part was an imaging part. So they took images of this sort of quarter of the night sky of 5 different filters, going from the U band, so the bluest wavelengths of optical light that we can detect under our atmosphere, all the way up to the Z band, which is almost into the near infrared. But in addition to these 5 imaging filters, they also took spectra of these galaxies. So once they knew the positions of the galaxies on the sky, they can then go and take a spectrum of it. And this is how they did it. It's a wonder of multiplexing. So if you want to assemble a large survey of galaxies, it's going to take you an awfully long time if you do one galaxy at a time. It's how early galaxy surveys were done, but now we've got much better at observing multiple galaxies in one shot. And there are different ways to do it. The way that Sloan did it is it takes this big plate that covers the focal plane of the telescope, and they plug these fibers onto the plate at the positions they know the galaxies are located. And this is done manually. Some poor soul has to do this every night, plugging these fibers. And there are about 800 fibers per plate. So in one shot, you can get spectra for about 800 galaxies. So over the years that Sloan ran, it eventually accrued spectra of around 1 million galaxies. That's a lot of galaxies. Okay, great. So we now have this large survey with both images and spectra associated with them. We can now start looking for mergers. Okay, so how are we going to do this? Well, there are 2 main ways that you can do this. Technique number 1 is using your eyeball. So you may be familiar with this classification system that Edwin Hubble came up with. So Edwin Hubble was the first visual classifier of galaxies. And he looked at the plates that he was taking. He identified that he could see spirals and barred spirals and ellipticals, lenticular galaxies, and classified them onto his famous tubing fork diagram. So we have this sort of broad brush classification system already present in our community. But it is a very big ask to get someone, even a graduate student, to look at 1 million galaxy images. That's bordering on slavery. So you have to come up with a cleverer way of doing it. And the cleverer way of doing it is by crowdsourcing the problem. So this was one of the first big projects of what has now become citizen science. This is the Galaxy Zoo project. It was really an inspired project. It was begun by a group out of Oxford University. And what their premise was it's very difficult to train a computer to classify galaxies. But the human eye is so good at doing this. And it really only takes a few seconds to distinguish a spiral, glass spiral, but computers, it's very, very hard to train them to do this. So what they did is they came up with this idea. They called this Galaxy Zoo, and it's a web-based project where the general public were asked to go, and they were randomly shown images of galaxies within the Sloan database, and they had to classify them. They had to say, you know, are these spirals or ellipticals, or can I see a bar in this? And when it was first begun, they assumed this would be maybe a 5 to 10 year project because they wanted to classify 1 million galaxies. But when this was launched in 2007, it just really took off. They had 150,000 volunteers. And within the first year, they already had 50 million classifications. So on average, every galaxy in Sloan had already been looked at 50 times by 50 different people and classified. So the classifiers were shown the image, and then this is the sort of the decision tree that they went through. They were asked, you know, do you see spiral arms? Is there a companion? If it's edge on, does it look like there's a rounded bulge or a boxy bulge? How many spiral arms does it have? Is there anything strange that might indicate gravitational lensing or anything weird like this? But one of the questions was, you know, do you either see a tidal tail or is there a close companion? So mergers were identified by the general public in this way. So there's a merger catalogue that came out of Galaxy Zoo. The crowdsourcing is fantastic, but it doesn't get it right all the time. So there's some cleaning up to do. And after the cleaning up, I came up with a catalogue of about 100 of these post-merger galaxies that I really believed. So there was a list from the Galaxy Zoo public volunteer team of about 3,000. I looked at 3,000 galaxies and tossed a lot of them out because a lot of them are pairs, and I was interested in, first of all, finding things that were fully merged together. So here are some of those images of the 100. So they're ever so nice to look at. It's not so onerous to look at 3,000 galaxies. And really, when there are gems like this in here, it's really a joy. Okay, so this is technique number 1, visual classification. The second technique is to do an automated selection based on measurements that we can make from the spectra of these galaxies. So the Sloan data reduction pipeline is able to identify where galaxies are in the sky. It reads the information on the plate. It can distinguish between stars and galaxies based on whether they're point source or whether they're extended. So you have your RA in depth of all the galaxies in your 1 million. And you also have spectra for these, so you know the redshift. Now, many galaxies that appear close on the sky are just chance alignments. So we're not interested in those. Those are contaminants for us. We want to know, of these close pairs, which galaxies might be truly interacting. So the way that we do that is we require that their redshifts are very close to one another. In fact, we use a tolerance of about 300 kilometers per second. Alright, so what we then did with this automated technique was we took all the positions of these 1 million galaxies. We pulled out all of the galaxy pairs that were both close on the sky. We had a threshold of 80 kiloparsecs. And they had the same distance, they had the same velocities. And we had 11,000 of those. Okay. We have 11 in this sort of pre-merger stage, and about 100 in this finally coalesced stage. Okay, fantastic. Now we can start to do some science. But before we start doing science, I would like to explain to you how we make our measurements. So this is a picture of a giant, what we call H2 region. So an H2 region means a big cloud of ionized hydrogen. In the center of this H2 region, there is very active star formation. The high energy photons from these new hot massive stars are ionizing the hydrogen around them. That's why we see all this beautiful emission. Okay. So astronomers have a way of measuring this star formation rate that I've mentioned before based on how much ionization we see. Now, I know this sounds like scary physics, but it's not too bad. So, and I apologize if you're getting palpitations of being taken back to the high school physics classes. Okay, but anyway, this is our schematic view of a hydrogen atom. Okay, so we know that the hydrogen atom has a proton in the center, and then it has one electron when it's in its neutral state. And that electron can be in different energy levels. It can't be just anywhere, it has to be in one of these fixed energy levels. Okay, so if I put hydrogen atoms near these hot, massive young stars, tons of photons coming off, it's easy for these photons to strip the electron off the hydrogen atom. So now I've got, in my gas cloud, I've got 3 electrons and 3 protons. Now, some of these electrons recombine with the proton. They're reunited. They make the atom once again. But what tends to happen is the electron, when it recombines onto the atom, it comes in at one of these sort of moderately high energy levels. But that's not the natural state that the atom wants to be in. So even though the electron kind of comes into here, it's then eventually going to decay. It's going to lose it. It wants to be at its lowest energy state. Okay, so it will decay down. And quantum mechanics tells us the rules about how the electrons can move and how they can decay and what the most likely decay pathway is. But when those decays happen, when the electron moves down these energy levels, new photons of light are given off at fixed wavelengths. Okay, so we get spectra like this. So for different chemical elements, we get these different bright lines in our spectra that correspond to photons being given off as electrons move down these energy levels. This is true not just for hydrogen, this is also true for any other chemical species that's present in this nebula. Okay, so what does it look like then when we take a spectrum of one of these star-forming regions? Something like this. This is actually a spectrum of one of the Sloan galaxies. So we just have here a measurement of how many photons are coming out, the flux, as a function of wavelength. So these emission lines here that are labeled are associated with hydrogen or oxygen, nitrogen, silicon, the different species that are present in the nebula. But importantly for us, we're going to measure how strong this hydrogen line here. It's labeled here as H alpha. So it's just one of the lines in the hydrogen spectrum. And there is a direct correlation between how many stars there are, how many of these high energy photons are given off, and the strength of this emission line. So by measuring the strength of this emission line, we get a measure of the star formation rate. Okay, so we're almost there. We're almost ready to make our measurements. There's one last thing that we have to do in the design of our experiment. Okay, so we have our merger galaxy now. And what we really want to know is how does the property of this galaxy in a merger differ from its isolated self? Now in the simulations, that's easy to do, right? You start off with your simulated galaxy in the isolated state, and then you just take a carbon copy and put it in the merger. Well, we can't do that in real life. So what we have to do is we have to try to identify as best we can the isolated counterparts of the galaxies in our merger. So what we do is for each galaxy that's in a merger, we have a measure of how massive it is. So in this particular example, this merger has a mass in the stars of 10 to the 11 solar masses. And it's in a redshift of 0.05. And then what I do is I go to my other sort of 1 million minus the 11,100 that I've got in my merger sample of isolated galaxies. And I find as many galaxies as I can with the same stellar mass and the same redshift. And I call that my control sample. So all of these galaxies, for example, have the same stellar mass and the same redshift as this one, but they're just not in a post-merger state. Then what I can do is I can say, all right, now if I want to know how my star formation rate differs in my merger versus my control sample, I'm just going to take the star formation rate I measured from this, which remember is just the strength of my hydrogen lines in my spectrum. I also have the star formation rates for all of my controls, which is the average of the star formation rates of all of these controls, and then I'm just going to look at the ratio of the two. That's my star formation rate enhancement. Fantastic. Okay. So now we can actually ask ourselves, in our merger sample, as a function of the separation of the galaxies, do I see an enhancement in the star formation rate? Well, we sure do. So this is our star formation rate enhancement. So if my galaxy merger had the same rate of star formation as my control, that ratio is just 1, slightly down. But what I see is that the blue lines are our data. If I'm out at very large separations, a few hundred kiloparsecs, nothing interesting happens. Okay? The average star formation rate is the same in the mergers and the control, so this ratio is down to 1. But as my galaxies get closer together, the star formation rate starts to get higher and higher and higher relative to what I would expect in my isolated galaxies. Okay, so we can actually detect this prediction from the simulations. There are 2 sets of simulation points on here, black and red. I'm not going to go into the details of this, but the bottom line is that the data actually follow very nicely what the simulations predict. Another thing that the simulations predict that I haven't talked about yet is that the mergers should change the chemistry of the galaxy. The reason is the following. If we ask ourselves where the heavy elements are, so, professional astronomers, we have this very biased view of chemistry. We have hydrogen, and we have helium, and then everything else we just call metals. Right? We just lump everything in this. We're so insignificant in the grand scheme of things. So we talk about the metallicity of a galaxy, and really what we mean is how much stuff do we have that's got an abundance, that has a mass greater than helium, relative to what we've got in hydrogen. That's what we mean when we talk about the metallicity of something. And those metals come from stars, from nucleosynthesis in the cores of stars. Okay, so if you measure the metallicity of a spiral galaxy, and you look at that metallicity as a function of the distance from the center, you find that the highest metallicities are at the center, and then it gradually decreases as you go to the outer parts. This is because there's been a lot of star formation in the centers of galaxies. So all of these generations of stars that have gone supernova, they've re-enriched the interstellar medium with these metal products, and we now see that in the gas. In the outskirts, the star formation rate is much lower because there's not so much gas, so the metallicity is lower. So we have what we call this abundance gradient in the metallicity. Okay, so when the galaxies interact with one another, I've talked about this bar and how this bar funnels gas towards the center, and this buildup of gas really star formation that we see. But this gas that's falling towards the center is coming from the outskirts, and that gas is fairly metal poor for the reasons that I just described. So now we're taking this very dilute gas and pouring it onto this, what was originally very metal rich gas. So another thing the simulations predict is that as galaxy mergers proceed, we should see that the amount of these heavy chemical elements gets diluted because of this inflow of gas. So we can measure that as well. Now, sorry, this figure up here is kind of faint. This is our spectrum again. When we go just go back. It's our spectrum again. So you'll see that in addition to the hydrogen lines that I've talked about, there are also lines from oxygen, magnesium, sodium, silicon, sulfur. So we can use these lines in combination with our hydrogen lines to measure the metallicity of this gas. Okay, so that's what we do. Now, I'm sorry that this is marked in some very unfriendly label. This basically just means, what is my change in metallicity? So just as here, I was looking at the change in the star formation rate as my galaxies get closer together. This next graph is the same thing, but it's for the chemistry, for the metallicity. So now what we can see is that as the galaxies get closer together, rather than an enhancement, which is what we saw with the star formation rate, we now have a depression in this metallicity. So again, another prediction from the simulations that's borne out. Okay, the last test we're going to try to make is to see whether we can identify galaxies where there is this black hole accretion going on. So we have this sort of general term in astronomy, which refers to the presence of a black hole and material accreting onto it. We call that phenomenon an active galactic nucleus, or AGN for short. So we think that essentially all massive galaxies have some supermassive black hole in the center. This is true for our Milky Way. Our central supermassive black hole has a mass around 4 million solar masses. And what recent research has shown is that the mass of the black hole, which is what is shown on this axis, seems to correlate with the mass of the central bulge. So in a disk or spiral galaxy, your bulge is relatively small. In a big elliptical galaxy, it's bulge all the way, there's no disk. So there's this correlation between the mass of the black hole and the mass of the bulge. So these black holes are present in essentially all spiral galaxies and all elliptical galaxies. But for the most part, they're not doing anything very interesting. But just occasionally, material falls towards the black hole and builds what we call an accretion disk. So this is an artist's impression, this isn't a real photograph. So you have a black hole in the center, and the material that falls close to the black hole makes this accretion disk as it starts to swirl its way down the black hole towards the center. And when that happens, we can actually detect the very powerful radiation that's associated with this accretion. These AGN, or active galactic nuclei, manifest themselves in a variety of different ways. One way is through X-ray radiation. So this accretion disk gets very, very hot. It reaches temperatures well in excess of 1 million degrees. So that is radiation we can see in the X-ray. Another way of identifying a galaxy that is in this switched-on AGN state is through the presence of these large radio jets. So this is an image of Centaurus A, which is typically considered an elliptical galaxy. It's got these dust loads as well, so you can argue about the morphological classification. But superimposed on this optical image, there are these color contours which are showing an image taken at radio wavelengths. So there are these enormous radio jets that far exceed the visual extent of the galaxy. And this is due to jets that are coming out perpendicular to this accretion disk that we see in the radio. So we can detect these sort of very luminous AGN associated with these very, very massive galaxies and massive black holes in ways like this. But for spiral galaxies, it's much harder. So this is an example of a spiral galaxy that has one of these AGN in it, right? But it looks completely unremarkable. You could not just visually say, yep, I can see that the black hole in the center of that galaxy is busy accreting material. You can't see it. And most spirals that are AGN are of this type, i.e., they may be doing something interesting, but you can't see it by just looking at a picture. When a spiral galaxy has its black hole turned on, we call it a Seyfert galaxy. We have a special way of identifying Seyfert galaxies. And again, it comes down to the spectra. So here are two spiral galaxies. This one is not accreting onto its black hole, and this one is accreting onto its black hole. So how do we tell the difference? Well, we basically measure the strengths of these different emission lines. Now, it's kind of hard to see on this graph, but in here, this is the spectrum I showed you earlier. There's this very strong hydrogen line, and then right next to it, you can barely resolve it, there's a much weaker line. That's a line from nitrogen. And in a normal star-forming galaxy, that nitrogen line is much, much weaker than the hydrogen. But when the black hole is switched on, the state of the photons is very different in the galaxy, so it means that the strengths of the emission lines change. So here is that same hydrogen emission line, and again, the nitrogen line that's right next to it. I don't know if you can see, but it's a lot stronger. So what we have to do is we go through and we measure the strengths of all of the emission lines for these 1 million galaxies. Now, of course, we don't do this by hand. We can do this automated fitting of the spectra and measure the fluxes. Now, this is work that was originally done back in the 1980s. And what you do is you on a graph, you measure the strengths of different emission lines. So I've talked about this hydrogen line, I talked about the nitrogen line. So this is the ratio of those two lines. And we also take the ratio of another pair of lines, one of oxygen and a different hydrogen line. And we make this diagram. Okay. The first version of this diagram, with a few hundred galaxies, looked like this. Each individual point being the measurements of the fluxes in individual galaxies. With slow, we have 1 million points we can put on here. So we can't even show all the dots anymore. We have to do it in contours. It's only when we get into these more sparsely populated regions that we can show the individual points. Okay, so what you can hopefully see on this diagram is this basic V shape, these two wings. And if you are a star-forming galaxy, you lie down here. And if you are an actively accreting onto your black hole type galaxy, then you are up here. So this is how we distinguish the galaxies in the nearby universe, or one of the ways that we distinguish whether a galaxy has its black hole active. Okay, so now we know how to do it. We go through, we classify all our merger galaxies as either star-forming, i.e. doing its normal thing, or AGN, i.e. the black hole is turned on. And the prediction from the simulations is that we should see more of the AGN in our merger sample. Indeed we do. So again, as a function of the separation of the galaxies, we just count up how many AGN we have. And then we count up how many AGN we have in our control sample. And we take a ratio of those two. If I have the same number of AGN in my mergers as in my control, that ratio should be down here at 1. And again, we can see this beautiful relationship between the separation of the galaxies in the merger stage and how many AGN we have. So as my galaxies get closer, then this final point here, this is for the galaxies that are fully merged together, I'm steadily getting more and more black holes actively accreting. And just sometimes you get really lucky. This is not my work. This actually worked from about 10 years ago because, as I say, you have to get really lucky. You can actually catch the two black holes right on the moment of merging. So this is an image of a very well-known nearby merging galaxy. It's a case where you've just got one single galaxy, so the two have merged. You can see very clearly there's a lot of leftover debris and tidal disruption. So this is a post-merger galaxy. And if you take an image of the center of this thing at X-ray wavelengths, where we're tracing that hot disk of material around the black hole, you can see two separate point sources. So this is where the two individual galaxies and their two individual black holes are coming in, and they're very, very close to merging. They're not quite there. Gets a lot of physicists really excited because these merging black holes provide the best possible laboratories for trying to detect gravitational waves. So the hunt has been on to try to find even more of these binary black holes. We have about half a dozen at the moment. They're very, very difficult to find. They're very, very rare. You have to really get lucky. Okay, so let me wrap up. The three sort of take-home messages, if you will. So first of all, mergers are really not that rare, and they're very important in terms of changing the fate of a galaxy. They can change both the morphology, but they can also do all sorts of interesting things to the gas inside the galaxy. When we have large surveys, like the Sloan Digital Sky survey, we really have a treasure trove of data to try to study these. And so I've shown you some of our recent research results tonight, where we've been able to trace what these gas flows are doing, how they feed star formation, how they alter the chemistry, and how in some cases they even lead to accretion onto the black hole. Thank you very much.
So does anybody have any questions for Sarah? John.
Sarah, if